Good morning. There are a couple of announcements to make for the class this morning. I wanted to point out to you that there will be office hours that I will hold this week, even though the lecturers will have stopped. And as far as the office hour on Wednesday, I'm tentatively changing it to the room that I've listed over here, which is one of the lab rooms that's not being used in the morning, so that Dr. Schabel, who will be beginning on Wednesday, has the room available for office hours for him. So unless you hear differently next Wednesday, for those of you who want to come to office hours, it'll be in BLSB. At the end of the lecture today, I'll try and talk a little bit about the midterm and try to answer some questions that you might have. And again, I'll be around. We have a review session on Wednesday, and if you have emails or questions, you're welcome to send them to me. I've been able to address most of them pretty quickly. The last time we introduced you to the concept of water relations, and I said that the concepts that deal with water relations apply to all living systems, not just to plants. And you were introduced to three different aspects of water relations. Psi, which is the overall water potential. That is the potential of water to move. Secondly, we said that if there were salts or solutes dissolved in the water, that gave us a number which we said was psi sub pi or sometimes psi sub s, depending upon what book. It's a measure of solutes. And third, we talked about the fact that there can be pressure, which is a turgor pressure, or tension, and that's like when the water column is stretched, with regard to the movement of water. And in both cases, this is a positive number, this is a negative number, but in both cases they are indicated by psi sub p. So you can have either tension or turgor pressure inside of a cell, and in both cases it's indicated by psi sub p. Now what I'd like to do is to put the three components together. Most of you who have read through the lab know what the components will be. And those three components are arranged in the following way: that the overall movement of water from one region to another is determined by adding the pressure potential and the solute potential. These two elements need to be added together. And the important point that I want you to understand is that these two elements by themselves don't determine which way water moves. They are only part of the equation, and the ultimate factor to determine whether water moves is the number that you get for the overall water potential. We're going to now explore this a little more closely, and you're going to have an opportunity in this week's lab, which students like very much because you, in fact, actually do experiments and get some really good answers. And for the experiment today, what I want to do is go back to the system which we had before, which was the guard cell system. And so I'd like to start giving you some real-life situations of water potential and letting you understand how it works. We said the guard cell system involved the guard cells plus the pore, and that these are part of the epidermis. And so what I want to add on for you is the surrounding epidermal cells in the leaf, if you pretend like this board is the leaf surface. So here we have now an epidermal cell. And for this discussion, I want to take you back to a point we made at the end of the lecture last time, which is that the movement of potassium into and out of the guard cells is important in affecting the psi. So potassium is the ion which we're moving across the membrane of these living guard cells. And what you need to understand is that potassium can move across the membrane either into or outside of the guard cell. When it's moved out of the guard cell, it's in the epidermal cells. And when it is taken up and the epidermal cells reduce their concentration, that's because potassium moves into the guard cells. So what I'd like to do, having given you that slight bit of background, is to make a table. And in this table, what we're going to do is to put some real numbers on the water potential equation and on the two subunits for a guard cell situation. And so we'll have psi sub pi, and psi sub p. And for this, we will divide our experiment into two portions. In one portion, the pore is going to be open. And in the other portion, the pore is going to be closed. And what we want to do is to look at these subnumbers plus the overall water potential in both the guard cell and the adjacent epidermal cell in the open and closed state. So on this side, we'll put the guard cell and the epidermal cell. And in the closed situation, we'll also put the guard cell and the epidermal cell. And now what I'd like to do is to begin to put some numbers on here for you that you can use in helping you understand water potential. And what I'll be giving you are several examples to help you solidify these concepts in your mind. The first thing I'd like to do is to look at the guard cell turgor pressure when it is open. We said before that the guard cell is open because of an increase in pressure pushing out on the membrane. So a reasonable value for the turgor pressure of the guard cell when it is open is 5 bars or atmospheres, depending upon, again, what our units are. And when the guard cell or pore is closed, we have lost turgor pressure inside, so a reasonable value of the change in turgor pressure would be 1. Now let's go up and look at the solute potential of the guard cell in the open and closed state and in the epidermal cell. When the guard cell is open, the potassium in the epidermis has been moved into the guard cell, and you would find then that the epidermal cell would have a lower level relative to the guard cell as far as potassium. How about in the closed situation now? In the closed situation, we're moving potassium out of the guard cell into the epidermal cell. And what you'd find in this situation is that now the potassium has increased in the epidermal cell. Everybody clear on this? And finally now, before we calculate all this together, let's look at the turgor pressure in the epidermal cells, that is the cells adjacent to the guard cell, when the guard cells are fully inflated versus when they are no longer turgid. And in that particular case, there's still going to be turgidity in the epidermal cells, but they're not going to be that great. 3, and in the situation where it is now porous closed, there is now a greater turgidity in the epidermal cell. And now what we want to do is calculate what the overall water potentials would be. We want to put these numbers into the equation to your right, or your left, sorry. And if we calculate that, a 5 and a minus 8, the overall water potential of the guard cell would be minus 3. 3 and a minus 4, the overall water potential of the epidermal cell would be minus 1. So in this situation, just dependent upon water potential now, water is going to move in to the guard cell, just as we've talked about before. And this puts it now in concrete terms with regard to the water potential. Now, let's reverse the situation. We've pumped potassium out. Water has left, presumably, and let's calculate what the water potentials would be. When the pore is closed, that is, potassium has been pumped out, the water potential will be minus 1. And when the pore is closed, the potassium has been moved to the epidermal cells, and the water potential now is minus 2. So in this situation, just following water potential, the water is moved from the epidermal cell, from the guard cell to the adjacent epidermal cell. Any questions on this? Yes?
What's determining psi p?
What is it? Psi p is determined by the fact that water is going to follow a potential with regard to its movement with regard to pressure, so that if there's no pressure inside and you have now an increase in solid potential on the inside, psi p will become more positive. And then water will move in until it reaches a point where no more water can be moved in because of the characteristics of the cell wall, and you've reached the maximum size of the cell. John will talk more about it later, or else we'll be here all day, okay? All right. So now you have this one situation where we have the water potential of the guard cell. This is a situation which you can apply, and I want to make sure you understand this, because this is a general situation of two cells being adjacent to each other and us trying to understand the water relations. There are many other examples, some of which will probably appear on the final exam, not on the midterm. And one of the examples that I want to bring to your attention that some of you are aware of, this is a plant called the sensitive plant, or mimosa. If it's performing the way we want it to perform, for those of you who are sitting up close, as I touch the leaves, they close. And the reason they close is because there's a decrease in turgor pressure inside the leaves. That is, water is leaving the leaf. Now, why does water leave the leaf in this particular situation? In this situation, what we have happening is that we first touch the leaf, and this plant is called the sensitive plant, and you're going to see it at the botanical garden when you go up there. So when you touch the leaf, what happens is you initiate a series of steps. The first step with regard to your touching, there's actually a small electric current. And in this particular case, the electrical current results in potassium moving from the leaves, or the leaflets in this case, into the petiole. And this is accompanied by a drop in turgor pressure. In the leaflet. And an overall decrease, or an overall change in psi, favoring water moving from the leaflet to the petiole. And what I'd like to do, and some of you have already anticipated this, is I'd like you, instead of having guard cell and epidermal cell, I'd like you to substitute in this table leaflet and petiole, and just go through an exercise where you put some numbers in. They can be the same numbers if you want from this table, or other numbers based on the physiological features, to understand that this table, this idea behind this table, applies to many different situations. Now, in your problem set, we ask you to calculate the water potential of a number of situations. And one situation which you are given to ask, as far as calculation is concerned, is a lake. That is an open body of water. That's essentially equivalent to a beaker of water. Beaker of water. Now, here we have our lake, and here we have our beaker, just to make it a little more lab-like. And this water here in the lake and this water here in the beaker both have a water potential. They both have a psi, although in this case, let's assume that some of the water from the beaker is from the lake, so they have the same water potential. And if I told you now that the solid potential of the lake, psi sub pi, equals -4, which would mean, since this is the same water, so you now know the size of pi, and I asked you to calculate the water potential given that information. Remember, water potential equals psi sub pi plus psi sub p. So in this equation, what I've done is tell you that for the lake or for the beaker of water, the psi sub pi is -4. How can you possibly arrive at the water potential when you have another unknown? And the answer is that in both the case of the beaker and of the lake, you have no possibility of increasing turgor pressure because there is no membrane. And neither of these two situations is under tension. You're not stretching the water molecules in any way. So in both of these cases, psi sub p equals 0. Because you cannot increase the pressure, nor can you put this liquid under tension. So for the problem set, when you are examining the questions regarding the open body of water, keep in mind that we are very easily able to calculate the water potential knowing just the solid potential, an important point. Okay, now what I'd like to do is to give you a relatively special case with regard to the water potential. And this is an important example because in the example that I'm about to show you now, the water potentials of both of these cell types is exactly the same, but they're the same for different reasons. And here are the two cell types. We're going to take a parenchyma cell. And remember, a parenchyma cell is living, so it has a membrane. Living cell having a membrane. And in this situation that I'm giving you, it is directly adjacent, in fact, it's touching a xylem element, which, as you will recall, is dead, no membrane. And what we'll do is make a table, and in this particular table we'll have the xylem, just slightly reversed as far as the order, and parenchyma. And in this table, we're going to look at the psi sub pi, and psi sub p. So first look at psi sub pi, and psi sub p. And what I'm going to say to you in the beginning now, and this is the part which I think is where there's the real lesson, is that the water potential for these two very, very different cell types, the water potentials are the same. So these two cells are in equilibrium. That is, there's no net change in the amount of water in these two cells. And for this example, since they are in equilibrium, this is regarding their water potential, we're going to give you a reasonable number for psi for these two cells, which would be -8. And now let's see how we arrived at this -8. Again, to remind you of the formula, psi equals psi sub pi plus psi sub p. How did we arrive at the 8? Let's look at the parenchyma cell. The parenchyma cell is a living cell. It has a membrane surrounding it. So as a result of having a membrane surrounding it, it is able to increase the amount of solid on the inside. So a reasonable value in this particular example for the amount of solid inside would be -11. Now, because it is a cell with a membrane, it has the possibility of increasing turgor pressure. So since we have these two numbers here, we're able to calculate what the turgor pressure would have to be, and the turgor pressure in this case would be 3. Pretty clear on that. Now, let's look at the xylem element. This xylem element has a water potential of -8, but it's dead. It doesn't have any membrane. So this xylem element is not going to be able to concentrate solids. And in fact, the concentration of solids in the xylem is going to be essentially what the concentration is of solids in the soil. Very dilute solution. So that water in the soil is just moved into the xylem without concentrating any of the salts that have to be in the soil. So a reasonable value would be -0.5, a very dilute salt solution or solid potential in the xylem. What this means then is that in order to have a water potential of -8, if you have a very dilute solid concentration, that means that psi sub p has to be -7.5. And this -7.5 is the tension. So the point that you should get out of this table is, although the water potentials might be the same for these two cells, the reasons for the water potential being the same, that is, the components, are different. And again, it is what the water potentials are, not what the individual components are, that determine which way the water moves, that determines the overall water potential. Make sure you understand this particular situation, because it's one where you're going to be spending other time looking at other examples of living cells next to perhaps other living cells, or living cells next to dead cells. Finally, what I'd like to do is to return to a situation which we gave you when we were talking about water movement in the plant last time, and I drew you the elements of the plumbing system of the plant. And those elements were the stem, the leaf, although not directly an element of the plumbing system, the atmosphere, the root system, and this was the stem. And we gave you some numbers for this particular example. I can't remember exactly, I think I said the atmosphere was -20, and the leaf was about -8 as far as water potential. Now what I want to do is to put some numbers on for the other two elements of the stem and the root system. For the stem, a reasonable value would be psi equals, say, -4. And for the root system, a reasonable value would be psi equals -1 for the overall water potential, or -2, something around there. Now what you should get out of this picture is that water is moving in the plant along a constantly decreasing gradient in psi. An important point. So it is moving from a more positive psi to a more negative side, from where there's a greater concentration of water to ultimately where there's a lesser concentration, or in this particular case, as far as water potential, this is really what we want to get you to know about. So these are the principal elements that I want you to get out of water relations. If you understand what we've talked about here, you should be able to do all the problems, and you should have an appreciation for water relations at the level that we want you to have for both the lab and for the final exam, where we'll cover water relations more heavily. Finally, what I want to do before we move away from water relations is to talk to you a little bit about the other transport system in the plant. We've talked about the xylem, where we have tension. What I'd like to do now is talk to you about the phloem. And to remind you, the principal element of the phloem is a living cell with a membrane. This is the sieve tube element. And for our understanding of how the phloem works with regard to water movement, we have to add a few other things onto this. The first thing I want to add onto it is a parenchyma cell. In which photosynthesis occurs. Next, I want to add on to it, because you understand from your lab that the xylem and phloem are together in the bundles. Running adjacent to the sieve tube element or sieve tube member is the xylem. And this could be either a vessel or a tracheid. And then at the bottom of the supply, or the bottom of the list here, we're going to add another parenchyma cell. But this will be a parenchyma cell in which storage occurs. So starch or sugar storage. And let's talk about how this works now. We'll write this down for you because it's not totally obvious. And by the way, this is something surprisingly as important as it was, which is still somewhat controversial, although most people agree that this is the way the phloem works with regard to water relations and with regard to water movement. At the top of the phloem, sugars which are produced by photosynthesis are added. Sugars are added to the sieve element. That is, they're transported to the sieve element. So at this point over here, we have sugars being produced as relation to photosynthesis. As a result, we now change the psi at the top, which is accompanied by water moving into the sieve element at the top. So not only do we have the sugars going in, but this is now changing the water potential and results with water also moving in from the adjacent xylem. Water moves in from the adjacent xylem. Now, as a result, what this does is this causes an increase in pressure at the top. An increase in pressure at the top. Now, what I want to do is to take you to an example that you're all familiar with, which is a garden hose. You know, if you take a hose and you turn it on, there's pressure at the place you turn the hose on, and at the end of the hose where the water comes out, the pressure is reduced. Well, this is exactly the same situation which is occurring in the phloem. We have high pressure at the top because we've changed, and we're changing the pressure down at the bottom. How are we changing the pressure at the bottom? At the bottom, sugars are removed. And they go into the adjacent parenchyma cell, crossing the membrane. This changes the water potential at the bottom. And water leaves, and pressure drops. Where does the water go? Well, we've now changed the water potential here in the xylem, in the sieve element, and some of the water goes back into the xylem again. So this is sometimes called the pressure mass flow model, pressure-driven. Pressure-driven mass flow, because we are carrying the sugars down from the point of entry into the phloem in a mass, and their movement down is based upon the fact that the pressure is higher at the top than it is at the bottom. Now, all of you have experienced this pressure in your lives. If you, on a warm summer day, are walking along a sidewalk and your feet stick to the sidewalk, or if you come back and your car is parked under a tree and you find sticky stuff all over the windshield of the car, those represent exudates from the phloem that have been produced by the pressure. The phloem is under pressure. And how does that pressure get onto your car windshield or into the bottom where you're walking? It gets onto it by the fact that there are a number of insects, I'll show you some pictures of them in a moment, a number of insects which feed on the phloem. And these insects Can you put the screen down, please? These insects insert their stylet into the phloem and then use the pressure in the phloem to essentially push the sugars through the insect. And while the sugars and the solution from the phloem are being pushed through the insect, it is then absorbing some of the nutrients for itself. But it doesn't absorb all the nutrients. So the nutrients are released, and I'll show you a picture of this in one moment, as droplets. And these droplets still contain sugars, and as they dry, they become sticky. For those of you who are biblical scholars or anthropologists or archaeologists, or just from the point of view of wanting to know something that's kind of interesting, it is claimed by biblical scholars that the manna that the children of Israel supposedly ate during their 40 years of wandering was actually this exudate, which was produced by these insects that would insert their stylet into the phloem. Let me now show you a few pictures of this particular situation. Here are the aphids, and what I want you to see is the stylet has now been inserted. Maybe we could just dim the light slightly. Thank you. Aphid is inserting its stylet into the phloem, and now if we look at a cross-section of a stem where the stylet is inserted, the aphid stylet is on the very top, and it goes all the way through a ray that you probably should be familiar with to the most recent phloem, as shown in the next slide. And in the phloem, in the sieve element, the liquid is under pressure, just as we described before, and it is pushed up into the stylet. The aphid doesn't have to suck it at all. It's pushed through the aphid so that if you look at the aphid, what you see is a drop of liquid exuding through its abdomen, and this liquid then contains a lesser supply of nutrients than entered the aphid, but still a high supply of sugar. So this is the way the phloem operates. It's a very controversial system in some ways. A lot of people are not sure that this is the exact method of operation, but right now it is the way that most people are interpreting movement in the phloem and trying to understand how this pressure arises in the phloem. Now finally, for the last thing I want to talk about here to you, aside from questions about what's going to be on the exam, for most of you, the topic which brings the second largest number of questions from you is my plants in my dorm room are not looking very good. And I was wondering if you could tell me what was wrong with them if I bring in a plant for you to look at. Now, in most cases, if your plants assuming they don't have a disease, a pathogen disease of some kind, or maybe being attacked by insects, in most cases, if your plant is not looking good, it is because they are suffering from a decrease in minerals, certain minerals that are required for its growth. You will recall from our very first day when we lectured about plants, we said that plants were unique in that given sunlight, water, and carbon and hydrogen and oxygen, that each plant, even the single-cell green alga, was a separate self-contained entity, a separate self-contained body, could manufacture its own food. And that statement is correct in a certain way, but it isn't totally correct, because in addition to carbon and hydrogen and oxygen, there are a couple of other elements which are required for the plant to complete its life cycle. And so what I'd like to do in the last 15 or 20 minutes of the class is to talk to you about essential nutrients for plants. And we can define an essential nutrient as an element without which a plant cannot complete its life cycle. Now, in most cases, no element is completely absent from the environment, and so the less than optimal doesn't result in the death of the plant. Less than optimal element supply doesn't result in the death of the plant, but results in things that are known as deficiency diseases. And this is what most of you are experiencing or encountering in the plants that you are growing in your dorm room, assuming that they're not pathogenized by either a microbe or some insect. The essential elements are divided into two groups, the ones that plants need to complete their life cycle. So-called macro nutrients or elements. And these are required in relatively large amounts. So perhaps 1 to 4% of the dry weight of a plant are composed of these macronutrients. And micronutrients. In contrast to the macronutrients, micronutrients are required often in vanishingly small amounts, often in parts per million. Now let's talk about what elements fall into the macro and micronutrients, the ones that are required for the plant to complete its life cycle. There's carbon, hydrogen, and oxygen, which are the ones that we talked about the very first mention of plants in the algae. In addition, there's phosphorus, potassium, nitrogen, sulfur, calcium, iron, and magnesium. These are the macronutrients which are required in relatively large amounts by plants, and their total absence of any of these will prevent the plant from completing its life cycle. Falling into the micronutrient scheme of things would be things like copper, molybdenum, sometimes aluminum. We have chloride. And then there are situations where we have some micronutrients. These are often used as cofactors for enzymatic reactions. In some plants, they also need traces of other micronutrients. And one of these plants is shown up here in front. This is a plant that many of you have seen before. It's called horsetail or equisetum. And for those of you who have touched it or you want to come up afterward and touch it, you feel it has a gritty nature to it. And the gritty nature is that this plant reflects the fact that it has incorporated into its body, it is necessary for this plant to have silica. So most plants don't need this, but particular plants such as this one, this horsetail, need it. And again, for those of you who are history buffs, silica is used. This plant is also called scouring reed because it was used by the pioneers to kind of scour their pots and pans out, kind of the ancient Brillo before we had Brillo for cleaning your pots and pans. Now, most students, once they're told that they have likely a mineral deficiency, wind up going to the store and buying a package of fertilizer. And usually that helps. And if you go into the nursery or wherever it is that's selling fertilizer and buy it, you'll find that there are numbers that are listed on the top of the fertilizer, such as 3, 12, 18, 14, 26, 85. I mean, these are sort of odd numbers. What do they mean? These numbers represent the ratio of potassium, phosphorus, and nitrogen in the bag. And depending upon what time of the year it is, whether you're trying to get the plants to grow or to make fruits, these ratios change. So you're going to see different fertilizers having different concentrations. Of these fertilizers in the world, if you were to just supply one particular element to increase the output of food in the world, the one that is most lacking and would result in the greatest increase in productivity, especially in developing countries, is adding nitrogen. This is the one shortage that is critical that affects the food supply of literally billions of people. Now, finally, let's assume that you put this fertilizer on your plants and they still don't look good. They're still looking funny. So at that particular point, I say to you, okay, let's go back to your plant, and I want you to make the following observation of the plant to help us decide which of the nutrients is missing. Obviously, it's not one of these guys over here. And this is what I want you to do. I want you to tell me if the oldest or the newest leaves are affected. The oldest or the newest leaves are affected. So let's look at a plant which has some nutrient deficiency, and you're going to go ahead and make these observations. So for this particular case, let's start out with your plant at time 0, or let's say 3 days after germination. So here we have our plant sitting here in the pot. We've now produced one pair of leaves. Now we'll let some time go by. And in this particular case, the plant has this first pair of leaves that it produced from before, this oldest pair, but it has also produced a second pair of leaves. And we let some more time go by, and this is what I want your observations to tell me. Here we have our plant. We have now the first or oldest pair of leaves which is produced, the second or next oldest pair of leaves, and in this particular situation, we have a third pair of leaves that are produced. If you could lower the screen again, that would be great. Now, what I want you to tell me, looking at your plants, is which leaves look crummy. Do the oldest leaves look crummy, or do the newest leaves look crummy? Which are the ones that have the greatest damage done to them? And why are we asking that? The reason we're asking that is because certain elements are always moved to the newest leaves. Whereas other elements remain in the oldest leaves. So let's give you an example. Calcium is a compound which is used in the cell wall. Let's assume that our plant on the left had a very, very minimal supply of calcium present in the soil. And it used up all of the calcium so that by the time we were producing 2 leaves or 3 sets of leaves, we didn't have any more calcium. In this particular element, calcium, because it is incorporated into the cell walls, it remains in the oldest leaves. It is immobile. So if the newest leaves look the crummiest, whatever element is missing from your nutrient medium can be described as being immobile. And this is important in help us narrow down what element it was missing. Now, let's assume that the newest leaves looked good. You had the same situation where there was a very small supply of whatever it was you were using in the soil. It was used initially in the first set of leaves, and then the first set of leaves started looking crummy, but the second set of leaves looked good. And by the time you got to the third set of leaves, leaf set 1 and leaf set 2, the oldest sets, looked crummy, but the third set looked fine. That's because the element is mobile, that it is moved to the newest leaves. So by knowing whether or not an element is mobile or immobile helps us to be able to determine what elements are with regard to what they might be with regard to the deficiency disease. Here we have now a series of plants. These are sunflower plants. You're going to have them in the lab today, which are growing in various solutions in which a particular macronutrient or micronutrient is absent, and you can see a difference in the plant. Here's an example of a plant where the element is mobile, so that the older leaves look crummy, but the newer leaves are still green. We've run out of the element, and the plant is constantly removing it and moving it up to the top. Here is another one. This is minus magnesium. Again, the older leaves look crummy, and the newer leaves look fine. Here's an example now of minus calcium, which I talked about before. The calcium, once it's incorporated into the older leaves, cannot move. And so it is the newer leaves which are being produced which have very big defects in them. And calcium is an immobile element. Here's a very typical symptom of iron. Iron is an element which is said to be semi-mobile. And in this particular case, when you run out of iron, and this is quite common here in California, the veins of the leaf appear green, but the actual blade itself is suffering from a deficiency disease. Knowing the concentration of nutrients in the soil is very important if you're a farmer or an agronomist. These are examples of the absence of zinc and copper, both micronutrients. The effects they have on tomato are profound, and they can greatly influence the crops, as shown in this one for broccoli, in which the broccoli flowers don't form when molybdenum is absent. And this one is copper absence in peas. If you don't have copper, you don't get proper peas formed. And the same thing holds with regard to boron in carnations and also boron in apples. And finally, just to complete it, here's the absence of boron in grapes. So these are important nutrients which are needed for the completion of the life cycle. And if you are raising crops, if you're a farmer, if something is going wrong and it's not a disease due to an insect or a pathogen, it most likely is a disease which is due to a lack of the right nutrients. So finally, what I want to just mention to you is something about the midterm. The biggest mistake that students make on the midterms are that they don't read all of the answers. They go through the answers, and the very first answer which they see, which may be correct, they circle. But the instructions are to circle the answer which is not only correct, but which is most complete. So as you go through the multiple choice, there may be several answers which are all correct, and there will be a bottom answer which says A, B, and C are all correct. Make sure you read all of the answers first, because that's the biggest mistake students make. This exam has 33 questions on it. They're worth 3 points apiece. The other big mistake that students make on the exam is they circle an answer when you are reading through the exam for the first time, and then within the last minute or two of the class, they cross out that answer and they recircle another one. And our experience has been that more than 80% of the time that you do that, you have circled the incorrect answer when you go back and change it quickly at the end. So that's just a bit of advice with regard to the exam. I'm going to have the review session. I'll take emails, so please feel free to contact me. And have a good luck on your midterms.